Hello everyone, we the team AP050 presenting our project Smart and Sustainable Agriculture using FPGA. Coming to the introduction, agriculture is the most important field taken by mankind worldwide. Smart farming has been introduced in the agriculture sector by integrating the technology. Production in the crops mainly depends on the interaction between the soil and plant properties. Maximization of production in crops directly reflected by the physical, chemical and biological conditions of the soil. The hours need to make efficient utilization of available human resources like water and fertilizers, which will increase the crop's yield and also makes the cost optimization. And for that we have addressed some problems in the agriculture sector, and also we have provided some solutions through our prototype. According to Bureau of Soil and Water Management of the Department of Agriculture, it is advised to be analyzed the soil in every 3 years. Macronutrients like nitrogen, phosphorus, potassium should be managed properly to get the highest yield. And mismanagement in irrigation also a major problem in the agriculture, which in turn shows impact on world resources. Delay in identification of weed and diseases due to pests also makes huge loss in the yield, and over and underutilization of fertilizers also makes soil unfertile. So by addressing the above problems, we have come up with our solution which performs around 5 tasks. The first one is crop recommendation based on the soil condition, and crop customized irrigation by considering the date of the planting and region of the crop, and also in-time weed detection and disease prediction along with 3 control measures. In stages wise fertilizer recommendation along with brands also it will recommend it. And the entire process can be monitored by the farmer through the website, and also we have provided the regional languages voice outputs.
Our project mainly consists of 3 parts: hardware part, cloud part and website part for the user interface. Mainly to come to the hardware parts, hardware consists of D10 nanoboard, Arduino Uno, sensors like NPK sensor, water level sensor, water moisture sensor and pH sensor, and electric connectivity sensor, and motor for smart irrigation, and solar panel for continuous power boosting for the battery, and powering for system in daytime. The D10 nanoboard consists of 2 parts, HPS part and FPGA part. FPGA part is controlled using Verilog, whereas HPS part is having an operating system. In our project, the complete processing and GPU access is done using HPS part. To use the block switches, we need to access GPU pins from HPS session, which had a computer vision supported operating system. For that, we installed a pre-installed image, and we modified system on chip raw binary file using the existed XFC version. We use Arduino Uno microcontroller to collect all the analog sensor data, and we send all the data using serial communication to D10 nanoboard. The RFS daughter card, we collected all the sensor data. We mainly used temperature data and humidity data from the atmosphere for displaying to the farmer in website. And NPK sensor means nitrogen, phosphorus and potassium, the main soil nutrients in the soil. So we basically collect the NPK data from the soil through NPK sensor, and we performed crop recommendation and further task using the sensor. pH sensor. From this pH sensor, we collected the pH saline H+ ions, means pH of the soil for crop recommendation mainly. It plays a crucial role in crop yielding too. TDS sensor, total dissolved solids. From this sensor, we collected electric conductivity for calculating the salinity content in the soil. Through this salinity content, a farmer can know about the percentage of salts in the soil. E-tape level sensor. By using this E-tape level sensor, we calculate the length of water, means the level of the water from the crop level. For some type of crops, it is necessary to maintain some level of water for better yield. For that type of sensors, for that type of crops, we used the E-tape level sensor. And moisture sensor. Using this capacitive moisture sensor, we calculated the moisture content in the soil, and basically some of the leguminous crops in India and most of all of the world, and some of the crops they don't need much water. They don't need to maintain much level of water. So for such type of crops, we used capacitive moisture sensor to maintain better moisture content in soil. Role of FPGA V10 nanoboard in our project. Parallel processing. Here we collected all the sensor data and we sent to the cloud, and we also send a camera picture daily at a fixed intervals of time, and we also performed weed detection simultaneously as well as smart irrigation daily throughout the day, and sensor data comparison. From the day 1 to day end, we performed smart irrigation. Here we imported a date, and throughout the date as well as we divided throughout the crop duration into stages. Through it, we compared each and every day sensor data to maintain the water level for the fixed crops, and cloud connectivity by using Python SDK and Azure storage blob client. We connected to Azure storage account, and using Azure IoT, we connected to using Azure IoT client. We connected to IoT hub. We performed weed detection using Azure API models for weed detection mainly, and these are the main things we performed in our through the FPGA board, and high processor performance really by using ARM processor in this V10 nano board. The processing, the speed is very high as it is 50 megahertz. All the tasks, smart irrigation, weed detection, and sending data within the time for fixed intervals of time, it maintained high performance. It maintained a good performance. We observed that. And comparability, basically our project is agriculture project. It had a 6-feet stand and a box which holding all the controlling part. The size of the board seems to be very pretty. It helps in making our model a good looking.
Cloud connectivity and Microsoft Azure. We collected data from FPGA like sensor data, RFS data, and crop image from camera module. We stored this data in Azure storage accounts using Python SDK and Azure blob client. And then we redirected the RFS data to Azure IoT Hub for the message inference. We deployed our crop recommendation and disease prediction machine learning models on Azure App Service. And we deployed a custom object detection model for weed detection using Azure Container Registries and Azure App Service. We then created a website and integrated all these APIs for the visualization and to perform tasks like crop recommendation, disease prediction, and daily data visualization for the farmer, and deployed it in Azure App Service. Additional information about our project. We included voice outputs in our website for the ease of use to the farmers, and we included weather forecasting in our smart irrigation and fertilizer recommendation systems, and we are using solar energy as our primary source of energy or power supply. In future scope of our project, we want to include a dynamic camera for complete crop monitoring, and we want to include a drone for weed detection and fertilization, and also we want to collaborate with agriculture scientists to get accurate data collection that would be helpful to the farmer.
When it comes to impact of our project, our system will act as digital assistant to the farmer. Through soil test results, it reduces the cost, and by implementing weed detection, it helps in growth of the plant. By implementing disease prediction, it saves almost half of the yield. By smart irrigation, it saves water, manpower, and farmers' time. When it comes to our project sustains communities, farmers, agriculture sectors, agriculture universities, and soil monitoring health services. So yes, we have successfully done our project by implementing crop recommendation, weed detection, disease prediction, smart irrigation, and fertilizer recommendation. Questions are welcome. Thank you.